So as we begin, let's think about the common ion effect. When we have two solutions, each with an ion that's in common, we'll look at that as the common ion effect. And one of the first examples reads, when we have a salt with an anion of a weak acid, it reverses the dissociation of the acid. And it literally does so by lowering the percent dissociation. Now let me make sense of what this sentence is saying. Let's suppose we have any weak acid. We can let that be represented by HA. The term weak acid is telling us, let's suppose we have an equilibrium where hydrogen ion and that conjugate base called A negative, whatever the last name is for that acid. Now, according to Le Chatelier's principle, if we were to apply a stress, and that stress would be adding an ion that's in common with this last name. Let's suppose I just take a salt called, of course now my pen doesn't work, let me try to find a better one. Let's say a salt, something like Na, and then I have A negative. So sodium A negative. It could be like acetic acid. This would become sodium acetate. Whatever the last name is, it just needs a first name. We need to call that a salt. But the stress would say, if I add to this weak acid equilibrium an ion that's in common with it, such as the last name, acetate, or whatever A negative is standing for, that's a stress. And of course, Le Chatelier says we're going to do the opposite to alleviate that stress. By forcing the equilibrium left, we're taking hydrogen ion out of solution. This then becomes less acidic, and that's the same as saying raising the pH. By adding a salt to the anion of a weak acid, we literally change the pH of our solution by removing hydrogen ion. You know, that same principle applies to salts with this, there's the bell, with a cation in common with a base. Now let's just use some generic chemistry here. Suppose we have a base, and we'll just let that be represented by B, and we place that into a water solution. We set up an equilibrium where conjugate pairs are forming. This would be Kb chemistry, simply because we're producing a hydroxide ion. It's telling us, what if we put in a salt who has the same first name as the base? Ammonium chloride, or thinking of something that's in common. Well, the stress says, well, what if we add more of that same first name? Literally, we force that equilibrium left, and when we do so, we remove the base ion, so it becomes less basic, or literally drops the pH as it becomes more and more acidic. So the common ion effect really is saying we're going to be studying an acid-base equilibrium. We're studying some sort of equilibrium, and then really, according to Le Chatelier, we cause a stress, and the stress is putting something in common with it and watching it shift from left or right, and then recalculating based on an ice chart. So as we consider the approach to solving common ions, it really is thinking about step one, what are those major species in solution? Are we doing Ka chemistry for acids? Are we doing Kb chemistry for bases? What is it that we're actually studying? Get up an ice chart. We know that if we're studying Kas, we want to consider hydrogen ions. They determine pH. If we're studying Kb chemistry, we're going to be determining hydroxide ions, because it will determine pH of a solution. And we just simply tabulate the ice chart, knowing that it's the E row that's of interest to a chemist, the E row giving us the equilibrium values when we go to calculate the equilibrium constant. Let's dive in with an example. I'll read it with you and just ask you to follow along. We'd like to know the pH of a solution by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate in enough water to make a 1 liter solution. And Ka is given to us 1.8 times 10 to the negative fifth. Step one, figure out the chemistry. What are the major species? What is it that's involved in this equilibrium? The weak acid is acetic acid. The very definition of weak says it sets up an equilibrium. It will do so by creating ions of hydrogen and acetate. The equilibrium is represented with a Ka value 1.8 times 10 to the negative fifth. But we also have a competing reaction. Into the same solution, we have sodium acetate. Sodium acetate here's one that works. Now this is a salt, and the very definition of a salt says 100% of it is going to ionize. It's going to give us sodium ions and acetate ions. There's no equilibrium for a strong electrolyte. It 100% dissociates. But there is an equilibrium for the acetic acid. Here's what we know. Sodium acetate, 0.3 moles in 1 liter, that's 0.3 molar. When it dissociates, we get 0.3 molar sodium ions and 0.3 molar acetate ions. Of course, this is the ion we have in common with the equilibrium of the acid. This is the concentration we know to be of the acetate ion. So the 0.3 molar I can carry down knowing that it's already in solution coming from being the conjugate base of our weak acid. We know the initial concentration to be 0.3 molar. This would be 0, 0 plus 0.3. There's the common ion effect. And that's why I'm just carrying down 0.3. As time goes by, the acid gets used, minus X, 0.3 minus X. We'll let hydrogen be X, and technically this should be 0.3 plus X. But here's where the math is made easier, assuming that 5% rule. The plus X and the minus X get tossed out. So in other words, when we are looking at the amount of acetate ion that's being contributed to this equilibrium from the weak acid compared to the amount of acetate ion coming from the salt, it's negligible. It's not worth adding into the math. Ka simply becomes products over reactants, and look what happens. 1.8 times 10 to the negative fifth is the Ka. Hydrogen is X. The common ion between the salt and the weak acid is 0.3 molar. And in this particular example, because we were given equal amounts, this also is 0.3 molar, the concentration of the acid. The math simply shows these canceling out, and X becomes the Ka of our weak acid. Remember, we let X stand for hydrogen ion. Negative log, the value that we found for Ka, and we'll find our pH of the solution. So far I haven't hit my calculator, but when we hit negative log of 1.8, E negative 5, the Ka value for our acetic acid, our pH comes out to be 4.74 pH units. And does that number make sense? Yeah, it's a weak acid. We need to have that in terms of and in the acid range of our pH scale. So here's what we've done. We consider the important equilibrium. The equilibrium that's going to determine the pH is coming from the weak acid. It had an ion in common with a salt. That salt was called sodium acetate. The concentration of the salt became the acetate concentration in this particular equilibrium. Because the amount of X was so small, we tossed it out and set up a products over reactants where Ka became directly the concentration of hydrogen ion. It was then used to determine the pH of a solution. Let's consider a next example. Let's calculate the pH of a solution containing 0.085 molar nitrous acid, it's Ka provided, and 0.1 molar potassium nitrite. Now think about the competing equilibriums. The weak acid, HNO2, is nitrous acid. Very definition of weak says it's going to set up an equilibrium. And when it does so, we get the two ions, the conjugate acid hydrogen ion, its conjugate base nitrite. It has a Ka value of 4.5 times 10 to the negative fifth. Oh, excuse me, I'll repair that right now, to the negative fourth power. Also in solution, in a separate scenario, we have its salt, potassium nitrite, KNO2. The very definition of a strong electrolyte says it 100% dissociates, so that if I had 0.1 molar potassium nitrite, it's going to form 0.1 molar of potassium and 0.1 molar of nitrite, the strong electrolyte. So therefore, this value, the 0.1 molar, becomes the value, we'll carry over here, 0.1 molar nitrite, the ion it has in common. Now the other thing we'll know is the solution started at 0.85 molar of the acid. And again, in this first example, I set up the ice chart and then described to you how we know to toss out X. We can assume that to be true throughout this entire series of problems. So I'm going to just record underneath that then the 0.085 molar. The value for nitrite, 0.1 molar, and we're going to let the value of hydrogen ion be represented by X. I know technically this should be 0.085 molar minus X, and this should be 0.1 molar plus X. But let's assume that the concentration of nitrite coming from this dissociation of the acid is so small, negligible, it's not worth measuring. The Ka value, 4.5 times 10 to the negative fourth, is equal to the products, hydrogen ion, nitrite ion, set over the concentration of the acid. Solve for X, knowing that X will give us the hydrogen ion, and that X that we solve for there can then be determined, used to determine the pH. So let's hit together. Please hit with me. We have 4.5 E negative 4 times our concentration of the acid, 0.085, divide by 0.1, and we get X, 3.825 times 10 to the negative 4. Negative log that answer, and we should find our pH directly, 3.42 pH units. Again, a number that makes sense for a pH range of an acid. Let's flip over and see what else is on our agenda here. A couple more problems on common ion. How about these? It reads, calculate the fluoride ion concentration and the pH of a solution that is 0.2 molar in HF and 0.1 molar in HCl. Now we've got to go to work thinking HF. This is not a strong acid. Therefore, it sets up an equilibrium. Therefore, it has a Ka value. Doesn't give it to us, we'll have to look it up. But HCl is the other ion mentioned. HCl is one of our 7 strong acids, therefore it 100% dissociates. No equilibrium, no Ka value for this particular reaction. Let me quickly look this up while we have our chart nearby. F is 6.8 times 10 to the negative 4. Alrighty. So here's the story. This guy, HF, sets up an equilibrium. in the same container is a strong acid that 100% dissociates. If I place in 0.1 molar HCl, I literally have 0.1 molar of the hydrogen ion and that of chloride. But of course, this is the ion that's in common with the weak acid. We're being asked to calculate the fluoride ion. If it had asked us for pH or of a hydrogen ion, there it is, 0.1. I mean, that's the major species. So tabulating what we know in common. Let me just rewrite our equilibrium since this is what we're considering when we solve for our math. The 0.2 molar was the concentration of HF. The contribution of the hydrogen ion is coming from the strong acid, 0.1 molar. Now, fluoride we can let represent X. We don't know its concentration. Now, technically, this should be 0.1 plus X. This should be 0.2 minus X. But let's assume that X is so small, so negligible in the amount it contributes to the equilibrium that we can simply toss it out. And we can solve for the fluoride ion, calculating X, and we can solve for the pH by knowing hydrogen ion directly. So the Ka I found for us 6.8 times 10 to the negative fourth is equal to the hydrogen ion times the fluoride ion over the acid, 0.2 molar. Solving for X, knowing X is giving us the fluoride concentration that we have in our equilibrium. 6.8 E negative 4 times 0.2 divided by 0.1. And we get a value of 0.00136 molar, the concentration of fluoride. And the other part of our question asks for pH, and that's negative log of the concentration of hydrogen ion. So 0.1 becomes the hydrogen ion, and of course this is written as 1 times 10 to the negative 1, so the pH comes out to be 1.00. Remember your 2 decimal place rule. pH of our solution, very strong acid, 0.1 molar, gives us a pH of 1.00. Letting X stand for fluoride, we set up our equilibrium problem and pulled out the fluoride ion. Friends, we'll try one more together, wrapping up our common ion lesson. At the end here, we'll have accomplished enough information to do lesson number 1 off of our assignment sheet. We're going to calculate the formate ion and the pH of a solution that's 0.5 molar in formic acid, provided for us, Ka, and 0.1 molar nitric acid. This sounds very familiar to the previous example. We have a weak acid placed in with a strong acid. Of course, the weak acid sets up an equilibrium. See that COOH? Right there is your ionizable proton. Hydrogen ion and HCOO negative, the Ka 1.8 times 10 to the negative 4. Nitric acid is one of our strong acids, 100% dissociates. The ion that these two equilibriums or these two reactions have in common is the hydrogen ion, the common ion effect. If nitric acid was 0.1 molar, let me get that back on, 0.1 molar, that's the value I carry over to the equilibrium concentration, the ice chart here. We'll let formate be represented by X, and 0.5 molar, the concentration of formic acid. The common ion in this example was the proton, the hydrogen ion. It will be used directly to calculate the pH. Just as above, it looks like right away I can say pH will be negative log of 0.1. pH will be given to us from the strong acid, 1.00. The amount of hydrogen ion that the weak acid contributes in comparison to the strong acid is negligible. Toss it out. And we can solve for our formate ion by setting up an equilibrium problem. 1.8 times 10 to the negative fourth, that was given to us as the Ka. concentration of hydrogen ion times the concentration of formate all over the concentration of the original weak acid, 0.5 molar. When we pull out X, we'll have the formate polyatomic ion. Whoops. 1.8 E negative 4, there I got it, times 0.5 divided by 0.1, and our concentration of the formate polyatomic ion, 9.0 times 10 to the negative 4th molar units, the concentration of HCOO negative 1. Being asked to describe the common ion effect, and we have just finished our Moodle lesson on the common ion effect, and just kind of thinking about what it means and putting it into a pretty concise definition. We'll say really it's the extent of ionization of a weak acid being affected by the addition of a strong electrolyte, some kind of salt with an ion in common. So let's go ahead and begin writing that in some sort of succinct sentence. The extent of ionization of some weak electrolyte could be a weak acid or could be a weak base, but that extent of ionization is decreased by the addition of a strong electrolyte that has an ion in common. Really is nothing more than an application of Le Chatelier. For instance, if we look at a weak electrolyte, such as HNO2, HNO2 is called nitrous acid. Nitrous acid is not one of our 7 strong acids, so therefore we know it's weak. We think about the Bronsted-Lowry equilibrium that sets up, forming a conjugate base called nitrite, and the acid ion called hydronium. Whoops. Hydronium is H3O+. I don't know why I did that. So here we have an equilibrium where the forward and the reverse reaction are competing here. Nitrous acid is a weak electrolyte. If we were to add, let's just say a salt, not an acid, not a base, but it has a common ion. Well, the ion here from this weak acid is nitrite. And a salt has any other first name, any other positive ion other than the hydrogen. Lithium nitrite, sodium nitrite, potassium nitrite, and I can just pick any positive ion and call that a salt, positive hooked to negative. And what we've done, if I just add this strong electrolyte, which is just any concept of an electrolytic strong salt, has this common ion effect. If we were to add sodium nitrite, the ion it has in common is NO2 negative. Think about Le Chatelier. If we increase the concentration of nitrite, the system wants to counteract that. The opposite of more nitrite is less nitrite, and therefore we know it pushes back to the left, and it decreases the ionization. Decreases the ions. The number of ions in solution decreases as I go back to the molecular form of the acid. So we've illustrated the common ion effect. We have a weak acid or a weak base, but an electrolyte that's considered weak, setting up an equilibrium. We place in a salt that has the same last name as a weak acid or the same first name for a weak base, doesn't matter. But we have that ion in common. Here it was the same last name. The nitrite pushes it back left, and we therefore have decreased the ionization. Any salt would have done the same thing. The effect of adding this salt is to increase the nitrite, and Le Chatelier shows how that reaction will accommodate that stress by pushing left. Does the pH increase, decrease, or remain the same when each of the following is added? Remember that acids and bases affect pH. So letter A, sodium nitrite, is a salt, and hydrogen nitrite is a weak acid. So think this through. The equilibrium is indeed of the acid affecting pH. And if I just show the simple ionization, just as we have done here, and again I eliminated the water, but just showing the acid ion and the nitrite ion. The salt, of course, NaNO2, has the common ion nitrite. If I increase nitrite by adding sodium nitrite to this equilibrium, remember this is strong. There is no equilibrium here, and this is a weak acid. So this indeed is where the equilibrium is lying, is with the acid, not the salt. The addition of a common ion forces the equilibrium left, and if I go left, we have less hydrogen ion in solution, so it becomes less acidic, or you can also call that more basic. Removal of hydrogen ion makes the solution become less acidic or more basic. The pH increases. It goes up on the number line, moving away from the acid range towards the base range. Let's peek at letter B. Here we have methyl amine chloride and a solution of methyl amine. Now you're not expected to know that name, methyl amine, but you do have an Appendix D. And I bet if you look carefully on Appendix D, you can find the name of methyl amine. This, of course, is a weak base. What do you see in that formula that we should recognize to let us know it's a base and not an acid? It's that nitrogen. Remember those lone pairs of electrons? Very good at attracting protons, and that's what bases do, don't they? They accept a proton. So here's the chemistry. We have this methyl amine, CH3NH2. It has a Kb value from your Appendix D. It is a weak base. This is the salt. This is the base. When we place this into water, we set up an equilibrium where the proton is transferred. We have base chemistry going on. CH3NH3 positive is the conjugate acid of methylamine, our weak base, and the conjugate here of OH negative. Now, what's the ion we have in common this time? In methylamine chloride, the methylamine is the common ion. So when we add methylamine chloride, we're adding positive, negative, that's the salt, that's increasing the concentration of this conjugate acid. Of course, Le Chatelier says that equilibrium will now push left. And if I'm pushing left, we're removing hydroxide ions. Removing OH ions makes the solution become less basic, or you can think of it as more acidic. And what happens to the pH? It begins to fall toward the acid range. Let's try another. Sodium formate in formic acid. Again, I don't know the formula of formic acid, but I have an Appendix D. Appendix D is the tool that could help me find formic acid's formula. Oh, approximately less than halfway down, I'm finding formic acid HCHO2. Formic acid is a weak acid. It's found on a Ka chart. So therefore, the equilibrium will have formic acid form its conjugate base, and the conjugate acid of water, hydronium. What ion do we have in common with the salt called sodium formate? The ion in common is the formate. So by adding sodium formate, the ion in common increases the concentration of the formate, that negative ion. Le Chatelier says it's going to push left, and when I push left, I'm removing hydronium ions. Removing hydronium makes it less acidic, or some people's minds just work like this. They say more basic, so the pH starts to climb toward the base range on the pH scale. Potassium bromide is a salt. Hydrobromic is a weak acid. Hydrobromic is not a weak acid, it's strong. Hydrobromic acid is HBr. So here's the kicker here. 100% dissociation. There is no equilibrium. See, I'm doing right myself a note. If there is no equilibrium means no double arrow. There is nothing to affect. I could add potassium bromide. Remember from our last chapter, potassium bromide has two strong parents, potassium hydroxide and HBr. Both of these are strong. So ultimately what we're telling ourselves here, there is no effect on pH. No effect because there is no equilibrium when a strong electrolyte. Remember, Le Chatelier only works for double arrows. If there is no double arrow, the only choice here is pushing 100% to the right. HCl with sodium acetate. HCl is a strong acid. Sodium acetate is a salt. Now I do not see any ion in common, HCl and sodium acetate. So this really isn't looking at a common ion effect. However, let's take a peek at what might happen. Here I have HCl, strong acid. Let me just kind of work this through. So 100% of this is going to dissociate. Strong electrolyte, 100% dissociation. So I have a pretty strong acid. This is definitely going to affect the pH to where it's in acidic range. Sodium acetate is the salt. Now I recognize this parent as a strong base, so no effect on pH. However, the acetate ion, its parent is a weak acid, C2H3O2, acetic acid. Well, that acetate, its parent is weak, so it undergoes hydrolysis. And when it undergoes hydrolysis, it goes back to form its conjugate, its weak acid parent, leaving the solution basic. How might adding sodium acetate affect this equilibrium? Well, if hydroxide is being produced by the hydrolysis of this weak conjugate base here of acetic acid, this acetate ion, wouldn't the OH, let me change color, wouldn't the OH being formed here consume or use up or hook to the OH, giving us a little water molecule? By adding the acetate, we're actually removing hydrogen from the hydrochloric acid. It's a competing reaction, isn't it? Not necessarily a common ion, but more considering a competing reaction. H plus is being removed, therefore, ultimately, this solution is becoming less acidic. You could think of that as saying more basic, or increasing pH towards the base range. Let's think this one through, number 13. We have our Appendix D in a calculator. We have a solution of potassium propionate. Potassium propionate is the salt, a strong electrolyte. And we have a solution of propionic acid. Now remember, this has a Ka value. It's found on Appendix D, so therefore we know this is the equilibrium. HC3H5O2 is a weak acid. It will form its conjugates, which would be the propionic acid conjugate base of C3H5O2 negative, and the hydronium for the conjugate acid of water. Weak acid, its conjugate base, a base, and its conjugate acid. We're ultimately trying to find the hydronium ion as our target so we can get out the pH of our solution. Initially, our acid is given to us as 0.085 molar solution. We know that this ionization would have no ions yet to be formed. We know that ions form by using the reactant, and I'm just kind of filling out my ice chart just as we had done in the last chapter. Ions get made and reactants get used. However, we're also adding potassium, who by the way its parent is strong, so no effect. The common ion here is the C3H5O2. That goes right here in the equilibrium. Oops, not there. The common ion is C3H5O2 negative. That addition was 0.06 molar. Alrighty. One more thing. While I'm getting this set up, we can find the Ka of propionic acid from looking at Appendix D. Propionic acid, about 80% of the way down that Appendix D page, I find it to be 1.3 times 10 to the negative fifth. Let me look again. 1.3 times 10 to the negative 5. There. Now, what can we make with some assumptions here? Probably pretty good assumptions. The value that is being used compared to the original values, probably negligible. The value of the ions forming is probably negligible compared to the overall answer of ionization. So when we set up our Ka, we're going to toss out the minus x and we'll toss out the plus x because, as we've learned in the previous chapter, the extent of ionization, especially with this negative fifth power, pretty safe assumption to toss out the x. Now typically, what we're saying, let me just kind of set this up. Ka would be equal to x plus 0.06 times x, the value of our two products, set over 0.085 minus x. What we're suggesting is that the value of x compared to these original concentrations is indeed negligible. So they're probably worth tossing out, and we would just get 0.06 times x set over to 0.085, making the algebra a little bit easier. X, remembering, is what our target is. We'd like to know hydronium so we can find the pH of our solution. So 1.3 times 10 to the negative fifth times 0.085 over 0.06 isolates our x variable. And hit that with me so I can be sure we get a common answer. I like calculator buddies. 1.3 times 10 to the negative fifth times 0.085 times, divided by 0.06. And we get an answer for X. X comes out to be 1.84 times 10 to the negative fifth molar units. Negative log that value, and we'll have our pH of our solution. Did you find the same thing I did, where pH is given to us as 4.73 pH units? Does that number make sense? Well, it does. We were looking for an acid solution. pH of 4.73 does indeed lie in the acid range. Shall we try another? A letter B. This time we're given triethylamine, which is a base, see that N? And a 0.1 molar trimethyl ammonium chloride. So the common ion here is in the first name. And keep in mind, this is going to be base chemistry. Trimethylamine, here's the methyl group in organic. There's the tri part, trimethylamine. See that nitrogen root word, amine. When it undergoes hydrolysis, sets up an equilibrium, forming its conjugate acid, CH3, taken 3 times. There's the extra proton added on to the nitrogen, leaving the solution basic, OH negative. The original concentration of our base, 0.075. The value of the hydroxide at equilibrium would be X. And at equilibrium, technically, this is minus X. The concentration of our salt is 0.1 molar plus X. So I just went straight to the equilibrium row. At equilibrium, this reactant got used. The products got made. The salt had the common ion of a conjugate acid. See this conjugate here? CH3 taken 3 times NH. Trimethylamine chloride. Well, we need a Kb value for trimethylamine. Appendix D, the Kb value, do you see it written here? 4.4 times 10 to the negative 4th power. Set equal to the products, 0.1 plus X times X over 0.075 minus X. Longhand algebra, we could pull out X, or we can assume the value of X to be negligible compared to the original quantities. So we could toss out the value of X. Instead of 0.1 plus X, let's write 0.1. And instead of 0.075 minus X, we'll make the assumption of the 5% rule and toss out the X. So algebraically, to solve for X, we have to hit the Kb, 4.4 times 10 to the negative 4th, times 0.075 divided by 0.1, isolating X. Let's hit and see what we find. 4.4 E negative 4 times 0.075 divided by 0.1, and X comes out to be a value of 3.3 times 10 to the negative 4th. When we negative log that value of X, we get something called the pOH. 14 minus that will find for us pH. So negative log my answer, 14 minus that, and how about 10.52 pH units? Pause and digest if needed. Pause the video and think this one through, and when ready, pick it up again. Here we have a solution made by mixing 50 mils of a 0.1 molar acetic acid with 50 mils of 0.2 molar sodium acetate. Why are we given those volumes and not the volumes of the other solutions? Any ideas? Think that through for a minute. Why would we be given volumes here? Well, let's just think that through here. We have moles. We could find liters times molarity to give us the number of moles of each, and ultimately moles in a new combined volume would kind of give us an idea of why the milliliters were actually put in here. So here, let's just kind of take a peek. If I have acetic acid, H, C2H3O2, in an equilibrium with its conjugate base, acetate, and the conjugate acid of water, H3O+. Alrighty. Let's just do a little side math here, and I'll just make it a little different color. Acetic acid, just trying to tabulate under here, 0.15 molar times 0.05 liters gives us, let me hit that for us, molarity times liter, we'll pull out the number of moles. 0.15 times 0.05, get 0075, did you as well? Alrighty, and here we have sodium acetate, so that's the common ion here, 0.05 liters, that's the 50 mils, of 0.2 molar, 0.05 times 0.2 is 0.01 mole. We just have a new combined volume. So I just really think about the number of moles of acid. Instead of 50 mils of an acid and 50 mils of the salt, what we're now doing is diluting it. So 50 and 50 is 100, so that's 0.1 liter. And that'll be 0.1 liter as well, and a new combined volume. So let's see, I have 0.01 divided by 0.1. This gives me 0.1 right back. So after the dilution, we have 0.1 molar of the acetate, and after the dilution, 0.0075 over 0.1, we have 0.075 molar. So all of that little dilution problem, you could have done it like this. We know this to be true. MV equal MV. The original molarity was 0.15. The original volume was 50 mils. What's the new molarity if the new volume is 100 mils? Same idea, MV equal MV. Molarity times liter of set 1 divided by the new combined volume of set 2 got me the new molarity after the dilution. So that's all we had to do is figure out the dilution, and now we're ready to do the ice chart. The Ka of the weak acid, acetic acid, Appendix A, 1.8 times 10 to the negative fifth. Ka will be equal to the concentration of the acetate, 0.1. Technically it's 0.1 plus X, but we'll toss that out, times X, set over the new concentration here, 0.075. So to pull out X, we take that Ka value, 1.8 times 10 to the negative fifth, times 0.075, divided by that 0.1. And what do we find for X? 1.8 E negative 5, that's the Ka, times 0.075 molarity, divided by 0.1. And I'm finding for the value of X, 1.35 times 10 to the negative fifth. Now X represents hydronium. So let's take the negative log of X and find pH. 4.87 pH units. What made this problem different? Before, we were not given volumes. We had a solution that was already given to us. The solution had two components. The solution had a weak base and its salt already. Letter A had a solution where they were already mixed together. What made letter C different is that the solution is being prepared, and the key word here is there's a verb. We're doing the mixing. The original concentration and volume. So we had an additional step. We had a dilution problem where we calculated the new molarity and used that as we proceeded with our ice chart. Pause the video and really just think this problem through, maybe even working it again. And when you have that ready, start up with the next problem. Calculate the percent ionization of a 0075 molar butanoic acid. The percent ionization given Ka is 1.5 times 10 to the negative fifth. Let's take butanoic acid, and maybe with the help of your Appendix D, we can find butanoic acid. C4 H7O2 is in equilibrium. Alrighty, setting up its conjugate base, butane O8, C4 H7O2 negative, and the conjugate acid H3O plus. If the original concentration is 0.0075 molar, the original concentrations of the ions are set to 0. At equilibrium, we would have 0.0075 minus X, and we would have X and X for the concentrations of the ions. I'm just going to work down here and then erase. Perhaps you want to work toward the bottom of the page. The Ka value, 1.5 times 10 to the negative fifth, set equal to X squared. And let's assume the 5% rule and just put 0075, knowing that we're checking the ionization anyway. So let's hit for X. We're going to hit 1.5 E negative 5 times 0.0075, square root that answer, and X came out to be 3.35 times 10 to the negative fourth. Remember, that's the molarity, where this is the hydrogen or hydronium at equilibrium. To find the percent ionization, we just simply want to compare this value of X to the original concentration. So to kind of continue that thought process, we take the hydrogen ion at equilibrium, or hydronium, same thing, and I want to just set that over the original concentration of 0.0075 molar. That was our weak acid initially. All right, so just keep in mind, we're kind of stressing here percent ionization, the hydrogen ion at equilibrium compared to the initial concentration of the acid expressed as a percent. Divided by 0.0075 times 100, 4.47%, which does indeed lie within the acceptable range of tossing out the X. (4.47% ionization). And the other part has us consider the following. Let's calculate that percent ionization, same concentration of the acid, but now we have the common ion effect. we're going to put in a salt called sodium butanoate. That butanoate right here, that's the common ion. Now Le Chatelier would suggest if we increase this, that's the stress of the common ion, we should decrease the ionization. So I suspect by the time we're done, we should have decreased the ionization through the concept of the common ion. So we have the same setup. Let me put that back up. We have H, C4, H7O2 in equilibrium with its conjugate base and the conjugate acid of water. Initially, we still have 0.0075 molar and no ions due to the equilibrium. At equilibrium, we would have 0.0075 minus X. We would have X and X ions. Then we add the common ion. We add the salt, 0.085 molar of that common salt. This is from the salt that is in common with the acid. What happens to the ionization? Well, here's that Ka, 1.5 times 10 to the negative fifth. We looked that up here. That's the Ka for benzoic acid. Set equal to 0.085 plus X times X over 0.0075 minus X. That's the true calculation, but let's make some safe assumptions. Let's assume that the percent ionization, it was already, and we predict it's going to be even smaller, that the value of X's can simply be tossed out. Putting X on a side by itself, we would hit 1.5 times 10 to the negative fifth times 0.0075 over 0.085. 1.5 E negative 5 times 0.0075 divided by 0.085. And for the value of X, I found 1.32 times 10 to the negative 6 molar units, which was the hydronium ion at equilibrium. We want to compare, to find percent ionization, the percent of hydronium at equilibrium compared to the initial concentration of the acid. So here we have the value of X, and X is representing hydronium at equilibrium. Let's set that over the original concentration of the acid. I'm going to run out of room. C4H7O2 initial, and express that as a percent. So I'll divide by 0.0075 times 100 for a percentage, and I found my percent ionization to come out to be 0.0176%. Definitely a smaller number, as we had predicted. Without the common ion, 4.5% ionized. With the common ion, less than 1% ionized, reinforcing the common ion effect in words that we had written for our first question. When we add a stress, the stress is increasing the conjugate base of this weak acid. We do that by adding a salt that has the same last name as the original acid. That forced the equilibrium left. When we push left, we remove hydronium ions, which of course makes the solution less acidic, which of course makes the solution have a lower percent ionization. We have worked several different problems on common ion effect, both in a NotePack lesson, and now we've tackled assignment 1. I want you to try the next set of problems on your own. There is no solution guide posted, but this is what we'll come back with tomorrow and do a homework check.